our CPE equipment has a built-in MIPS processor, which would have done a stellar job as a workstation processor just several years ago. So it's incredible what the hardware guys are doing.
Of course, what you're able to put in a little box now. So you mentioned Coverity, and at this point I'd like to switch gears a little bit and give our audience an introduction to what Coverity is about. And so if we could go to the case study slide. This slide outlines basically why Coverity is around. And we're around because software defects are very costly. And in fact, this case study is not a customer case study, it's a personal case study, and that we understand very personally at Coverity the cost of a defect. And what you see here is what happened to us a bit more than a year ago, when a very important customer of ours licensed our product and unfortunately had a defect in our technology. And you can see there from the flow that through the technical support interaction and then having to fly out one of the founders of our company and a chief architect to debug that problem on site, spending days there trying to track that down, just like Gordon had to track down his memorable defect. Of course, this ended up being a memorable defect for us, and finding that it was a heap corruption issue, a use after free in a third-party library that we link in. But of course, the customer doesn't care if it's third-party or if you wrote it yourself. And you add it all up, and it cost us over $50,000. And that's just taking into account the salaries and the flights and the hotels. That's not taking into account the opportunity cost of these very smart people working on debugging issues instead of new feature development and doing the creative things that developers like to do. So if we go to the next slide, we provide a static source code analysis tool. And the benefit of static source code analysis tools, at least from a promise standpoint, is that they can find defects in the coding phase of the development process. You don't have to run the code. You don't have to have test cases to perform static analysis. And that way you can find problems in an entirely different way than you probably traditionally find those defects. And it's earlier in your software development lifecycle. Defects that you find with static analysis, they point to a specific line of code. If it's finding a defect in the code, there isn't the process involved of observing the symptom at runtime and trying to map that back to the actual source code construct that was causing the failure. It's all right there. You see the problem in the code, and you can fix it. And it's systematic. It can apply the analysis even-handedly over all the code, analyzing 100% of paths in the code base, something that your test suite isn't able to do because it's impossible to execute the code in all different execution environments. If we go to the next slide, though, the reality of most static source code analysis tools to date, and they've been around for a long time. In fact, Lint was introduced in 1978, and it's probably the most well-known static analysis tool. But unfortunately, it's not used in every software development process today. And one of the reasons for that, we believe, is because of the high levels of signal-to-noise ratio, or flipped around, too much noise. These tools tend to put out a lot of warnings and not a lot of real defects. And as such, when a developer looks at the tool, they see report after report that is just stylistic type of warning, not a real defect that they believe can impact the runtime of their program. And because of this, they stop paying attention to the tool. So that is what I like to say is the leading cause of death of a source code analysis implementation in a development organization is this problem of false positives. And there are other problems as well in terms of making it very difficult to integrate these tools into build environments because you have to point it at the source code. And they require, because of these false positive problems, a lot of configuration and a lot of tuning. Sometimes it won't be scalable. Depending on the algorithms used, they might work very well on thousands of lines of code, but not over hundreds of thousands or millions of lines of code. So as a result, people haven't widely used source code analysis. Until recently, if we go to the next slide, where we've developed technology out of a computer systems lab at Stanford that addresses a lot of these problems. And we've gone about it with a very systems approach, meaning from day one in the lab, we have been focused on analyzing large systems software. In fact, Linux was our first target, and analyzing it with the purpose of finding defects in a scalable way and finding defects with a very, very high signal-to-noise ratio so that we have mostly bugs and not a lot of false positives. Now, you have to pair that with the fact that you need to do sophisticated analysis because developers want to find sophisticated defects in the code. They aren't as interested in the ticky-tack kind of problems. They have plenty of things to worry about, so they want to know about issues in the code that are going to have significant runtime impact, things that are going to cause the program to crash, things that cause data corruption, concurrency type of problems. These are the things that developers want to see. And that's what we are able to provide now through our static source code analysis technology. So at this point, with that introduction, I'd love to turn it over to Gordon to quiz me a little bit and ask me a few questions about source code analysis before we open it up for general questions.
Thank you. So Ben, what do you see as the future evolution of static source code analysis? Is it, are we at the point where we're as good as we can get, or is there more room for improvement?
Well, we're definitely not at the point where it's as good as it can get. It's very good, and I think it's finally gotten to the point where it's practical to use in development environments, such as your own. But I think the number one thing we hear from our customers is, what new types of bugs can you find for us? What are the new ways you can find defects in our source code? And we're left to split that up into two categories, essentially. One is finding defects of the same types that we find today, new ways to find null pointer dereferences, new ways to find memory leaks, new ways people are leaking memory in their code based on the type of idioms that they use. And then there are also new types of bugs entirely that have to do with new programming idioms. For example, COM, for people developing in the Microsoft environment. And so we see a lot of requests for new types of bugs, finding more. They love what they see already, but they just want to see as far as they can push the source code analysis. What's interesting about that is, I think one thing that's hindered source code analysis for a long time is the prevailing mindset that these tools are very noisy. People think of source code analysis and they think of GCC's compiler warnings or lit-like tools that are awash with lots and lots of stylistic type of warnings. And because of that, that's really hindered our ability to push forth and throw out the craziest ideas in source code analysis for people to use. Because anytime you throw out anything that might have a high false positive rate, you get a lot of resistance because people don't necessarily trust the technology. One of the exciting things that's happening is we're seeing development organizations now believe in source code analysis and believe in its potential, and that gives us a lot more legroom to work with them to show them the latest of our techniques and the latest things we're trying to find with source code analysis.
So what do you see coming out of the academic world that might be applicable to source code analysis in the future?
So Dawson Enga, who's the professor behind this research, has always been really focused on finding bugs automatically since he's